Swayam Prabha. Digital India. Educated India.
So the next presentation is from National University of Singapore from our group, and Professor Mathpati, who is an associate professor at ICT Mumbai, and he's spending some time at National University of Singapore and working on a pharmaceutical project. So he's going to make the presentation. So Prof. Mathpati, please.
Yeah, very good morning to all of you. The slides are visible?
Yes.
Yeah, thank you. So today I'm going to talk about our work on high fidelity modeling of electrochemical synthesis with respect to pharmaceutical manufacturing. And I thank the PAC Asia coordinators for providing us with this opportunity. So continuous flow chemistry is important from pharmaceutical perspective because in most of the cases, the batch operations have issues such as inconsistent product quality, as well as they are processing large volumes at a time. So there can be some safety issues as well. But if we can shift to continuous flow chemistry, we can have higher throughputs for the process while working with very low inventories at any point of time. So we have an advantage of process safety and added throughput, so capacity enhancement. And all the process parameters are controlled within a narrow range, so that helps to achieve the consistent product quality as well. And changeover from batch to continuous also helps in miniaturizing the equipment and improving the energy efficiency. So with these advantages of continuous flow chemistry, many alternatives are presently being evaluated at R&D and pilot scale in pharmaceutical and fine chemical industry. Another domain area which is being explored compared to the synthetic organic chemistry is electrochemical ways of manufacturing certain pharmaceutical APIs or intermediates. The advantage of electrochemistry is it can be operated at milder operating conditions of temperature, pressure. And in case of redox reactions, the redox agents which are being used in conventional processes are stoichiometrically in large excess. So one can minimize these agents, and once we minimize this, then the further processing to eliminate those excess reagents will also be taken care of, and that reduces the waste generation. And one can improve the process selectivity by using electrochemical methods. And there are many commercial applications of electrochemistry in commercial scale because of low volume, high value products. They become economically competitive in terms of other synthetic chemical routes. So here are some examples of products which are being manufactured at commercial scale as well as at the pilot scale. So the major process variables when we talk about electrochemical manufacturing are temperature, which governs the activation energy and rate of chemical transformations. And in addition to governing the rate, that also controls the diffusivity, the diffusion of the species towards the electrode surface. Another is residence time. The residence time effect is prominent because more the residence time, we get better convergence. But more residence time may not always mean that we enhance on the selectivity as well. So there is some trade-off, and one has to really optimize the residence time as well. Third is the current density. So the amount of current that we supply to the system decides the rate of electrochemical reactions at the electrodes, and that helps us to understand the quantum that we are supplying versus what is the rate of the radical generation. And these radicals are eventually going to react with our other organic species in the bulk to give us the desired product. So the rate at which these radicals are getting generated versus the rate at which they are going to get consumed is also an important aspect one should consider in process development. Fourth is the substrate ratio. So that is the ratio of your redox agent versus your organic molecule that you have put into the system. So again, this ratio helps us to understand the product yield that we are going to get and the selectivities we are going to achieve. So if I take lot of organic content and very less of redox reagent, then I will enhance my selectivity, but the downside is I will have lower product yield and the separation cost will be high. And there are many reactor configurations available from which one has to choose when doing the scale up of such process. And the reactor configurations are dependent on whether you are using any membrane in between the two electrodes. So that classifies as divided or undivided cell. Then the hardware selection. So whether we want to have just a parallel two plate electrolyzer or we have some guided flows such as spiral flow reactors or serpentine channel reactors. And this decision affects the mixing, mass transfer, and residence time distributions in the system. Again, the way we apply current, it can be either we can apply constant current to the system or we can provide the pulsation. So the pulsation is important in modulating the electrochemical reaction at the surface. So high pulse will generate radicals at a faster rate, and the low pulse or off mode will help the electrode surface to replenish. And there are different electrode designs which are used, and even the material of electrode is also crucial. In some cases, the electrode can be porous, and in some cases, we can have a customized electrode which is built using 3D printing technology. And these 3D printed electrodes help in terms of localized mixing as well as improved surface area. And after all these decisions are made, then to get the capacity, whether we need to have multiple reactors which should be placed in series parallel, and what should be the electrode area to volume ratio. So this electrode area to volume ratio is nothing but how much inter-electrode gap that we are going to plan. And that again depends on the diffusivity of species. So it becomes a very complex process of decision making when we want to commercialize any electrochemical synthesis from lab to pilot or commercial scale. So in the present work, we have taken a generic reaction scheme in which we are considering there is one anodic oxidation taking place and radicals which are generated by anodic oxidation of some molecule A that will create a radical C and one positively charged ion E. And this positively charged ion E migrates towards cathode to produce some stable product G. And our organic molecule B in the bulk reacts with the radical to produce the desired product D. So this is our desired reaction in the bulk. And when this desired reaction is taking place, it is also generating one free radical. And this free radical reacts with again radical C to produce a neutral species. And there is one side reaction where the C can self-polymerize to produce an impurity I. So selectivity is defined in terms of how much D we are producing with respect to I, and the product yield is in terms of how much D we are getting with respect to the amount of B at the inlet. And the conversion is defined in terms of the amount of B which is getting converted in the system. And another conversion that we define is the anodic reaction. So conversion with respect to A and conversion with respect to B. So there are two different conversion values. product yield, and selectivity. And these constitute our performance parameter in terms of reactor design. And the rates of different processes are given here. The first two are written in terms of the Butler-Volmer kinetic parameters for the electrochemical reactions taking place on the surface. And the other three are the bulk reaction, which are modeled as power law. And in this particular work, we have evaluated two different designs. One is the conventional flat electrode system, where two electrodes are separated by a distance d, which is 4 mm in the present case. And another design is, in this design, we are putting an internal guiding channel such that it becomes like a serpentine flow path. So both these designs are actually going to differ in terms of the cross-sectional area available for the flow, which is much lower here. So you have higher velocities going in the system with more or less same amount of residence time. And these are the governing equations in the system, where in addition to solving the flow in the domain, one has to also account for the current distribution. Because of the reaction and current we have supplied, there is a current distribution in the domain, and this current distribution also affects the rate of surface reactions. And the radical generation rate is in turn going to affect the other bulk chemical reactions, which are modeled here. So there is a transport of dilute species one has to model, and these reaction terms in the transport equation, they depend on the current distribution as well as the velocity profile in the domain. So the flux is proportional, or it is dependent on the diffusivities, also on the mobility of the ions or species due to the velocities in the system. So it becomes a very complex multiphysics problem where there are three multiphysics coupling. One is the flow equations and the species transport, because in species transport, if your ion is charged, so the charged ion will tend to move towards the preferential electrode. Then the current distribution is also dependent on the reactions taking place. So that is another. And in the bulk, species transport and chemistry module are coupled together in this rate equation. So this is a detailed view of what is happening in the reactor. So for a conventional flat electrode system, we have simulated using 500 seconds of residence time, and the reaction mass properties are density of 800, viscosity of 0.5 centipoise, and the conductivity was taken as 2 Siemens per meter. And here what we can see is, as we are putting in the material into the reactor, so this is the profile of A, in which we can see that as it is moving towards the outlet, there is a surface reaction taking place at the anode, which is the top surface. So this is the entire is the top surface, and there is a depletion of concentration due to reaction. But this species A is a charged species, negatively charged species, and hence it has a preferential direction of transfer towards the anode. So here near the cathode surface as well, we can see a slightly reduced concentration due to preferential migration of these ions. So all these effects are very well captured by this high fidelity modeling approach, and we can get the convergence of A happening in the system. Second is this conversion of B, that is our main organic reactant, which we can see is getting reacted near the anode surface. So B reacting with the radical C is happening in the anodic region. Although it is a bulk reaction, most of the C radicals are concentrated near the anode. So we can see that most of the desired reaction is taking place near the anode. And this is the concentration profile of our desired product D, which is also getting formed in the anodic region. So this is how we can see that all the reactions and the transport of these species based on their physical properties gets captured in this computational framework. And this is the serpentine channel design. We have compared it with the same residence time of 500, and accordingly the flow was adjusted, and the applied current is 40 milliamps. So again, here we can see the transport of species A taking place in the system in a serpentine way. And the only difference compared to the conventional flat system is there is a more cross-sectional uniformity at the outlet in serpentine design compared to the flat system. And this serpentine design provides about 33% of product yield compared to 26% in case of the parallel flat plate system. So serpentine design, the mixing and surface renewal near the anode helps us to get more product yield compared to the flat electrode system. So this is how two different configurations could be compared based on the CFD analysis. Now we will look at the parametric sensitivity with respect to different operational variables. So here we have done the comparison with respect to flat design and the serpentine flow design. And this is the applied current. So if we increase the applied current in the system, we are generating more radicals C from A, and those radicals C react with the organic molecule B. And hence what we can see is as we increase the current, we have more conversion and product yield. But the selectivity is inversely related, because if you have more localized concentration of C, there is a higher probability of C reacting with itself to produce impurity I. And hence the selectivity drops if we increase the current. So for selectivity enhancement, one need to operate at lower current densities, and to improve the capacity and reduce the downstream processing cost, one need to operate at the higher current density. So again, there is a trade-off which will be decided based on the overall economic analysis. Second is the effect of residence time. And it can be seen that residence time, with increase in residence time, we have higher conversions and the product yield, and selectivity is more or less unaffected by the residence time. So increase in residence time is going to be a beneficial aspect in terms of having more throughput from the reactor. Third is the inter-electrode gap. Now, inter-electrode gap is a very complex variable, because once you change the inter-electrode gap, you are also changing the available volume in the system, and hence residence time also indirectly gets affected. So while doing this inter-electrode gap analysis, we have also changed the flow rates in such a way that the residence time is kept constant. And what we could see was at lower electrode gap, the diffusional barrier is small, and hence we get more product yield and the conversion compared to the higher electrode gap. And selectivity can be again seen to be in a very narrow range of 0.48 to 0.454. So again, selectivity is less affected, but lower electrode gap gives us a benefit in terms of increasing the conversion and the yield. The effect of temperature is mainly dependent on the activation energy that we have in the system. So these activation energies of desired and undesired reaction will decide whether we can get improvement in the selectivity with respect to temperature. The product yield and this conversions are fairly constant with respect to temperature, because the conversion of A is a surface phenomena, and that is mainly governed by the current that we have applied, and that decides the rate at which the C radicals are getting generated, and that will in turn decide the product yield we get from the system. So selectivity can be handled in a better way by changing the process temperature as well, based on the case study that we have taken. Another parameter is the ratio of our organic molecule to the redox reagent that we have in the system. And if we have less organic reagent compared to the redox agent, then we have more localized concentration of the radicals and selectivity is low. And if we can enhance the availability of our organic molecule in the anode surface region, that will help to improve the overall rate of this desired reaction and suppress this undesired reaction. So having very high concentration of B will help us to improve the selectivity, but there will be a lot of B which is going to remain unconverted, and hence the product yield goes down as we increase the CB by CA ratio. So if we wish,
Can you please wrap up? I think
yes, this is last slide. Yeah. So to conclude, what we can see is CFD can handle a complex interaction between flow, current distribution, and electrochemical reactions. And we cannot have any particular optimum condition which will help us both based on product yield and selectivity. So one has to decide which is the most important parameter, and hence based on that should optimize the system. And these are some of the references. We would like to acknowledge the funding support from Pharmaceutical Innovation Program of Singapore for this work. And yeah, thank you.
Thank you very much. Thank you, Professor Pati. In the interest of time, I think we can move on.